Hi everyone, this is Carlos with the EVapMass Science Support Team, and today we are going to be looking at EvapMass, a minimum mass of planets predictor. EvapMass predicts the minimum mass of planets in multi-planet systems using the photoevaporation-driven evolution model. So what that means is for this code to work correctly, we need to be looking at a system where there is at least two planets, one being below the radius gap and one being above the radius gap. This radius gap refers to the gap in our understanding of the universe when it comes to rocky exoplanets, where we have found tons of exoplanets below 1.5 Earth radii, such as Kepler-36b, and tons of exoplanets above 2 Earth radii, such as Kepler-36c. But we have not found very many in between that gap, and we are not sure why. So what we want to do here is we want to answer the big question. Given the photoevaporation had to completely strip the planet that resides below the radius gap, how massive does the planet above the radius gap need to be to retain its hydrogen-helium envelope? In other words, what EvapMass aims to do is to figure out if we have some system like this, and we have a planet like Kepler-36c, that is super close to its star and only about 3 Earth radii, how massive does this planet need to be in order to retain its atmosphere? And we ask this question because for rocky planets close to their star essentially evaporates away their atmospheres through its radiation, otherwise known as photoevaporation. You can think of Mercury as an example. So Kepler-36c, does it have an atmosphere? Yes or no? Let's find out. First thing we need to do is we need to telecode if we are looking at an iron rock core or a water rock core. We are looking at an iron rock core, or we're going to make that assumption, and we're going to say it's 1/3 iron and 2/3 silicates, rocky silicates if you will. We need to give it some time to evolve, i.e. the system. So we're going to give it 100 million years to evolve. Next thing we're going to do is we're going to feed it stellar and planetary parameters. Here we are feeding it all of the stellar parameters, everything from mass, effective temperature, radius, and even the age of the star, because this is actually important because we're talking about planetary evolution. And here we are going to give it the parameters for Kepler-36b, the smaller of the two and the closer to its star planet, and Kepler-36c, the bigger of the two and also a little further away, as you can see here. Now that we have given it all of its parameters, let's find out what the minimum mass of Kepler-36c needs to be consistent with the photoevaporation model. So again, we are going to feed it all the parameters. We're looking at all the mean values for our parameters. We tell it we are looking at Kepler-36, the star. We add our planets B and C with its radius, period, and their associated error bars. And we also feed it the mass, radius, effective temperature, and age of the star itself. These next three lines are functions that are a part of the EvapMass package, and they essentially check that everything we are doing is correct so far, i.e. we're using a planetary system that will work for this code. So here we are saying in this system, after we did all this, we know that everything is correct. Please tell me which of the two planets is more likely to retain its atmosphere, which in this case would be Kepler-36c because it's bigger and therefore has a stronger force of gravity to hold its atmosphere in. Now here we are saying, can you please check that everything is correct so far? And if everything's not correct, raise a flag. If everything is correct, please tell me the median mass of my planet. So after one calculation, we have found that the median mass for Kepler-36c is 5.7 Earth masses, and this is the median mass that Kepler-36c would need to have to retain its atmosphere. But one calculation is never enough, especially not in science. So we're going to redo it 1,000 times. We're going to run 1,000 samples. One big important part here Here we used 1,000 samples, but a value should be chosen such that the upper limit is converged, and that is up to you when you start doing this with your own star systems. So we ran 1,000 times. Now we can go ahead and make a histogram. So here in our histogram, we have concluded that the 95% upper limit to be consistent with the photoevaporation model is 4.96 Earth radii. In other words, for Kepler 36c to maintain its atmosphere, it needs to be at least 4.9 Earth masses. That is shown here by this black dashed line, and the actual mass of Kepler 36c is this blue dotted line, which is about 8.08 Earth masses. In other words, in this notebook we have shown that Kepler 36c is likely to have retained its hydrogen-helium envelope, i.e. its atmosphere. So yeah, that is EvapMass. It's a great tool. I had a great time doing this tutorial. I learned a lot. And yeah, if you guys have any questions, comments, or concerns, make sure to follow us and DM us on Twitter at ExoPlanetModels, or you can comment below, or you can send us an email. Yeah, peace.